In this lesson, we're going to be taking a little step back from writing our own C# scripts and instead take a look at some of the other scripts that can be found within the Tanks game. When implementing audio into games, it's likely that you'll need to understand and sometimes even edit and use scripts written by other developers. So we're going to be talking about how we can read and understand code and scripts written by other programmers. We're also going to look at when it might be best to let a trained and dedicated professional programmer implement particular aspects of our game's audio over us in order to produce the best results for our game's development. Finally, we'll also look at some methods we can use if we do have to implement audio into an unfamiliar script ourselves, if we absolutely have to. So far, we've implemented 3 different audio clips into the Tanks game, and whilst they've varied in difficulty level, they were all done completely within new original scripts that we created ourselves. We used basic data types such as integers, strings, and floats, tools provided by Unity's APIs such as pre-programmed functions like the start, update, range, and log functions, as well as Unity components such as the audio source component. But we haven't yet needed to use other C# scripts written by the developers of the Tanks game to get our own scripts to work and play our sounds when we want them to. However, eventually when implementing audio, we'll usually get to a point where we need to use the game's custom-built mechanics rather than just Unity tools to trigger, influence, or control our audio in some way. This could be to trigger a sound, adjust a property of an audio source, or apply an effect such as a reverb to the entire output of our audio. If we were using a custom-built game engine instead of Unity, most, if not all, of our audio would have to be implemented to fit within the game developer's code, systems, and mechanics that they'd built specifically for their game. So we're going to need to recognize the difference between audio that we can implement ourselves and audio that will only work if integrated with other game mechanics. Now, to understand these different concepts of audio implementation further, I have designated the names general and custom implementation to the following definitions. The first, general implementation, refers to audio that can be implemented into a game and work as intended, whilst only using the tools provided to us inside of Unity or any other engine we choose to make our games with. As mentioned earlier, all of the audio we've implemented so far can be considered general, as we've only used code we've written ourselves in order to listen back to them at runtime and make them change dynamically to suit the game. For example, we implemented the sounds of the power-up objects without us needing to know how they provide a boost in power to the tank's fired shells. We did use its trigger area for our sounds, however, as Collider components are provided to us inside Unity's editor, we can still consider this general implementation. Custom implementation, on the other hand, refers to audio that requires the use of a system created by code that was written specifically for the game we're building in order to be played as intended. This is often needed for audio that is to be changed in some way by the game in real time to sonically communicate a game-specific mechanic to the player via audio. So for example, you may have a game with a variable like the player's health. You may then wish to use that variable to increase the volume of a heartbeat sound when the player's health is low and they're close to losing. A good example from our game might be added sounds of sparks, bursts, and busted gears rattling against each other coming from a tank's engine when one of them is close to losing the last of its health. Well, in order to tell those sounds to play and loop, we need to ask a few questions. How and where is the health of a tank measured? Assuming it is a variable of either the float or int type, do I have access to this variable? Does health subtract instantly, or is there a quick fade from one value to another? How can I trigger my sound to play? Is there a function that triggers when the health reaches a particular value? And how do I tell my sound to stop? Is there a way to detect when a tank has been destroyed? You get the idea. There are lots of things for us to consider. So what can we do if the sound or music we're implementing falls into the custom category? Well, it depends on the audio itself and how it has been designed to be played and function within our game. In order to discover what our audio clips need to work, we're going to need to learn, even at a very basic level, how to understand code that controls our game's main features. So in order to demonstrate how you might read through a foreign C# script in Unity, I'm going to be taking a look through the tank shooting script that can be found attached as a component to the prefab file of the tank that our players can control in our game, which is called Complete Tank. To find this script and the prefab in your project, navigate your way through the Assets folder of your project and go through Tanks, Completed Assets, and the Prefabs folder. From here, select the Complete Tank Prefab, and in the inspector, select Open Prefab. Then scroll down to the bottom and you'll find a script called Tank Shooting. So go ahead and open the script by editing it. So now that both you and I are looking at the tank shooting script, I'm going to show you some things you can do to learn what's happening inside this script and any others you might come across. The first thing we could do is very simple. Check the names of the variables and functions. As we can see at first glance, this script is using a lot more variables than we usually do, all of which have been named to represent their purpose. We can tell by reading the names of variables such as m_max launch force and m_max charge time that these are likely to control how the shells are fired from the tanks. We can see that they are float variables based on the values set and the data type float written beside them. We can also see that these have all been made public. Now this could be for two reasons. One is that they are to be interacted and tweaked with by other developers in the Inspector tab in Unity, which can be very helpful for testing out how the shells fired from the tanks feel and how easy or difficult it is to destroy another tank. Being able to adjust these values in Unity's Inspector makes it a lot quicker to test and adjust these values, something we touched on in the last module. And the second reason may be to allow these variables to be used by other scripts. So in another script on the Complete Tank Prefab, we'd be able to create a reference variable of the tank shooting type, just like how we made variables of the audio source type in the first lesson of Module 2. Then we could use getComponent in, say, the start function to get an instance of this script, and then we'd be able to access any of these variables by referencing this script using the dot operator next to it and the name of the public variable we would like to access. Notice also that all of these variables' names begin with a lowercase m followed by an underscore. Now, this is something you may see other programmers do to the names of the variables that they declare directly in their class, as opposed to inside a function. This is so that when another or the same programmer sees a variable being used in a script, they can see whereabouts in the script the variable was first declared. The only exception here are these three variables in the middle. They don't have an M at the beginning of their names because they were actually created by myself in order to give us more mechanics to interact with and add audio to. In hindsight, I probably should have included the M to keep things consistent. If you wish to, in order to help you organize your scripts and identify your global variables from your local ones, feel free to include the m_ prefix to the names of any variables that you declare within classes as we progress through the course. Quick tip: variables declared inside of a script are also sometimes referred to as fields, which you may have heard myself say from time to time. It can get a little confusing to refer to the same thing, such as variables, by other names such as fields, properties, which we touched on in the last module, and even members, which is a more broad term for variables. So underneath this lesson, I've included a link to a guide that explains the minute differences between different variables and the names used to describe them. The second and more obvious way to find out the purpose of a section of code is by reading programmer notes. As we learnt back in the C# basics lessons, we can write notes or comments beside our code without affecting them by writing 2 forward slashes followed by our message. This is something that becomes more and more common and more important when working with bigger scripts and larger development teams, as sometimes the names of functions and variables don't make things clear enough for others to understand their purpose at a glance. Take a look at line 17, for example. Here we find a variable called timer. Now, whilst its name tells us that it is to be used as a timer, we wouldn't know the exact purpose of this timer if there wasn't a note next to it. However, we know now that this variable will act as a timer that tracks the length of time that a player holds a power-up boost for. Sometimes we may want to learn about how a variable is being calculated to see if we need it to control or influence a piece of audio we wish to play. One way to learn about how a variable is used is to simply double click on it. This will tell Visual Studio to highlight any references to that variable in the script. Let's take the m_charge speed float variable as an example. We already know, thanks to the programmer's notes, that m_charge speed will hold the speed that the shell will travel at based on the amount of time the player takes to charge a shot. So now we have an idea of what this variable is used for, but how is this script able to calculate the speed value that this variable will hold? As well as this, whereabouts in our script is the calculation made? Well, let's double click on the variable to highlight it, scroll down and look out for any more highlights in the script. And there, we can now see that Visual Studio is highlighting to us that this variable is being used inside of the start function. From here, we can see how it's being used. Thankfully, we have another programmer note that is telling us what is happening on this line in this script. But let's pretend for a second that we were not lucky enough to receive a note by our fellow developers here. Well, we can see just by looking at this line of code that a calculation is being made thanks to the division and the minus operators. By taking the difference between the minimum and maximum force variables and then dividing that by the maximum charge time variable, they're able to produce a value for the charging speed variable. And because this line of code is written inside of the start function, we know that the calculation is made once on the very first frame that this script is active for. Another method we can use when learning about someone else's code is to write our own. Remember, by writing the debug.log function, we can not only feed the value of variables into our console in Unity, but can also discover when they are being called. So let's say that we want to find out the value of the m_current launch force variable and see if or when it changes during runtime of our game. Well, the best place to start would be inside of the update function, as we know that it will run our function on every frame of the game. This way, if a change is made to the variable, we'll be able to spot it as it is made. Now we can see that this variable is being used in this function already and that it is being set new values to hold thanks to the equals operator following its name. So let's write our debug.log function at the very bottom of this function in order to make sure we're checking its value after it has been updated. Then inside the parameter brackets of the log function, we'll tell it to print the value of the m_current launch force variable inside Unity's console tab. Let's then save and jump over into Unity. So now let's open up the console tab, play our game, and see what values we're given. Okay, so we can see that the m_current launch force variable starts at a value of 15. Now, based on its name, we might assume that the purpose of this variable has something to do with holding whatever the current value of force is that will be applied to a fired shell. So let's test this and see if the value changes at all if we fire a shell. Okay, so the value changed, but it didn't change by much. Now let's see what happens if we hold the fire button. Okay, this time we can see it increases gradually all the way up to about 30 before resetting back to 15. Notice how whilst the value did increase, it was also set back to 15 after every other frame change. Well, this could be for a couple of reasons, and it's not very clear to us right now why this might be happening. So let's go back into our script and see if we can change anything to make it a little clearer. Okay, so currently we're calling our debug.log function on every frame. Because of this, it is a little bit difficult for us to see inside the console tab when it is exactly that our variable is changing values. So there's two quick ways we can limit the amount of times the log function is called as well as when. One option would be to limit the update function to only call log if a particular condition is met using an if statement. That condition could check for a particular change in another variable's value or the m_current launch force variable itself. The variable that we use would have to depend on how we believe this variable works. We know that it increases if the player charges a bullet, so maybe it would be worth calling our log function only if the m_fired boolean variable is at true, for example. The other option would be to simply call debug.log from another function. This is the option I'm going to take. So I'm going to cut the function from the update function and paste it inside of the start function. So now it's in the start function, it should only be called once rather than every frame. After saving my script one more time, I'm going to go back into Unity to see if this makes a difference. Okay, so let's see what happens when I play the game. So after waiting a few seconds for the first round of our game to start, and for the game to activate our two tank objects, and thus our tank shooting script too, we see our message appear. However, despite the fact that we put it inside the start function, which runs only once on the first frame of the game that our script is active for, we see the message appear twice. What does this tell us? Well, it tells us that our start function is being called twice because the one message we wrote has appeared twice. But how can the start function run twice if it's programmed to run only once? Well, rather than just the start function being called twice, it is very likely that the entire script is being called twice. Don't forget about the update function too. The fact that we saw it repeat the value 15 to us, whilst it was also seemingly changing the value of the m_current launch force variable at the same time, suggests this too. So how can the entire script be repeating our functions twice every frame? Well, because there are two instances of our script being used in our game. Remember, there are two tanks in this game that both inherit from the complete tank prefab file that has our script attached to it as a component. So both tanks have a copy of our script that they are each playing, and thus functions such as start and update are being called twice. The reason why I'm highlighting this might seem a little pointless to you, or maybe you were able to work out why our debug.log function was being called twice before I could explain it to you. So why am I telling you this? Well, when troubleshooting your scripts, sometimes the issues that you're trying to fix might be because of things outside of the script itself that you're working on, such as how it is being used in your Unity project and its relationship to it as a whole. Things like using the script twice can easily be overlooked or forgotten. So if you ever find yourself trying to learn about a script function or variable, fix an error, or trying to learn and understand a little bit more about how someone else's script works, it helps to remember how the script is being used inside of Unity. Now that we've understood the m_current launch force variable a bit better, we can remove the debug.log function from the start function. Now, if you're ever looking through a script to see if a specific term, variable, or function has been used, Visual Studio has a way of searching for that term. Just like inside a browser, you can press Ctrl F on a PC or Command F on a Mac at the same time to bring up a search window in the top right corner of your script. Now, seeing as this is the tank shooting script, let's say we wanted to find out where and how this script fires a shell. Well, first off, we can assume that this behavior is being triggered by a type of function, so now we know what we're looking for. And assuming that the function being used has been given the name fire or something similar, we can simply search for it to find where it was created as well as where it has been used. So let's type fire into the search window. The search window then takes us to the earliest line in our script that contains the word we typed into it. Now, the word fire is used a lot of times in this script, as we can now see thanks to Visual Studio. Right now, we're mostly looking at variable names and comments containing the word. So if we want to see if a function exists at all with that name, we can click on the right arrow at the top next to the search bar. Now remember, function names usually start with a return type before their name and are followed by a pair of parameter brackets after. This, of course, is only when they're declared within our script. If they're being called to run by our script, we won't see a return type, but we should still see the parameter brackets. As you can see on line 54, because the word fire is followed by brackets here, that tells us that it is in fact a function. Now, just by looking at what we found, we can figure out a little bit more about how this script works. So we can see that the fire function is being called within the body of an if statement. That if statement is being checked within the update function. Great, so we know that so long as this condition is met, the fire function will be called. And so long as our script is active in our scene, the condition will be checked constantly as the game plays out. Let's take a closer look at the condition, or rather the two conditions that our if statement is checking for. The reason why I say two conditions is because thanks to the two ampersands, we now know that the if statement is checking for two conditions to both be met at the same time before it will run the lines of code underneath it. The first condition is checking to see if the m_current launch force variable is ever equal to or greater than the m_max launch force variable. The second is checking to see if the m_fired variable is ever false. Remember, we know that it is checking if it is false rather than true because the creator of this script added an exclamation mark in front of the variable. So if both of these conditions are met, the fire function is called and triggered to run. But what exactly does this function do? Well, now that we know that a function called fire exists, let's keep scrolling to find where it was declared inside of our script. Quick side note, the reason why we know that this function was declared within this script and the main class inside it is because there is no class name written before the name of the function on the line that is being called. We only see the name of the function itself, fire. Remember, functions declared from other scripts will start with the name of the class that they were declared within, just like how the log function we've been using was declared inside of a class called debug, and the range function was declared inside of a class called random. So if we keep scrolling, we will eventually find our function declared near the bottom of the script. From here, we can see the fire function perform various tasks such as altering variable values, spawning shell objects, and more. So thanks to the use of the search bar, we discovered that not only does a dedicated function exist for the purpose of spawning and launching shell objects in our game, but we also learned that this script is checking every frame to see if and when two particular conditions are met to trigger the function and call it to run. The last thing I want to quickly do is test this function to see if it actually does trigger every time a shell is fired. So just like we did earlier, let's call the debug.log function at the bottom of the fire function, and let's give it a message along the lines of shell was fired. Again, it's up to you what you write here. Let's then save our script and jump back into Unity and our game. Okay, so let's fire a few shells and see if the message appears. Great, as we can see, the function calls the debug.log function to display our message for us. Once again, let's make sure we're being thorough with our testing and also fire a few shells with our other tank, as well as a few charge shots too. And again, we see our message display as we predicted it would. Excellent. So those are just a few ways you can search through a script created by another developer to learn about what each part of it does. Now that we've learned a few things about our tank shooting script, let's see if we can use it for some custom audio implementation. We'll start with this fire function and use it to play the sound of a tank firing a shell. First things first, in order to do this, we're going to need an audio source. So, as we've done so in the past, let's make sure that the prefab of the complete tank file is open and add an audio source component to it. We're also going to need to assign an audio clip to it. The one we'll be assigning to it is called shot firing. So once you've added your audio source, search through the audio clips within your project for that clip. And just like we've done with the rest of our audio sources, let's disable play on awake, make the sound 3D, and finally remove volume attenuation, just like that. Let's quickly save our prefab to make sure those changes have been made and then jump back into our script. Okay, now we know the first thing we need is a reference to our audio source in order to control it from within this script. So at the very top, let's make some space underneath the rest of our variables. Let's create a private audio source variable and call it source for short. Next, inside of the start function, we actually need to get our audio source and assign a reference to it inside of our newly created but currently empty source variable. So let's set source to get a component and give it the type we're looking for, which of course is audio source. Finally, the last thing to do is tell our source to play. So let's scroll down to the fire function, which we intend to use to trigger our source to play, and replace the debug.log function with source.play. And with that, we can save our script. So one more time now, if we fire a few rounds from either of the tanks, we hear the audio clip play. Great. So this example was obviously a very simple one that we were able to make work with a basic understanding of C#. However, sometimes the conditions you're looking for in order to trigger or control your audio might be a little bit more complicated. Sometimes systems for certain mechanics span across multiple scripts and rely on C# features that we haven't yet looked at, such as arrays, lists, constructors, raycasts, and loops, just to name a few, all of which aren't easy to pick up and understand straight away from the simple methods we've been using. Not to mention how a different game, genre, and development team will drastically affect the scripts in layout, organization, purpose, complexity, and more. So sometimes it becomes important for us to recognize when the implementation of audio is better left to the person or team who created the scripts that the audio needs to work with. Programmers will likely know the code inside and out and be able to get quicker and cleaner results than us. And we won't need to spend time analysing and probing the scripts they've written in order to understand how they work. That being said, if you are in charge of implementing audio at any level, it can be a great help to get an understanding of how some of the core scripts of your game work in order to effectively work with the game and understand how your fellow developers like to approach certain tasks and challenges. If you are able to understand the code of your game, even if only slightly, it could be a great benefit for both the developers and the audio team to effectively implement audio and help improve how dynamic and interactive it can be. So with all of that being said, when it comes to custom implementation, it's good to know your limits and for the sake of your game's quality, know when to share the responsibility of certain tasks. And with that, you should have a clearer understanding of audio implementation at a deeper level. Now we can implement audio for certain purposes on our own, or we can use other systems built by other programmers to trigger our sounds. We can utilize the names and locations of variables in other scripts, as well as any notes left by programmers to learn the purpose and function of the script we're looking at. And we can also test the purpose of functions created by other programmers by debugging a variable being used inside them. Now that you've got an idea of how you can approach other scripts, I encourage you to dive deeper into the tank shooting script. Doing this will help you learn more about how it recognizes and manages changes in its value data variables in order to know when to trigger a shell to fire, and know by how much force that shell needs to be fired at. Once you've done that, take a look quickly at some other scripts to see what tools and techniques you recognize are being used in them. You might be surprised at how much you're able to understand and pick up already. Then once you've done that, take a nice well-earned break and we'll be waiting for you in the next lesson.